participants. Our next speaker here is Shahar Chaikin. Welcome.
Hi, everybody. So first of all, I'm very excited being here, and thank you all for coming. I would really appreciate your feedback after this talk, because this is a study in preparation. And I also would like to thank, before I begin, to ECCWO for funding my arrival to this place. So thanks. And let's begin. So today, there's increasing evidence suggesting that warming coincides with forward range shifts. Here is one famous, relatively famous example by Pinsky et al., showing the relationship between latitudinal shifts of 9 different marine assemblages against the change in bottom temperatures. And you can see the positive values in the y-axis will denote assemblages that move towards higher latitudes. And what they found across 360 marine taxa is a positive relationship, meaning that increasing bottom temperatures correlate with forward migration. And you can see here one interesting outlier in orange. That is the Gulf of Mexico that probably prevents the forward shift due to its semi-enclosed nature. We also know that warming coincides with abundance changes. Another interesting study by Hastings et al. Shows the relationship between abundance change and the spatial position of different populations. So values on the x-axis that above 0.5 denote forward populations. These are populations that are facing in the forward range of their range, and values below 0.5 are equatorial populations. And what they found in this study across more than 300 different marine taxa is a positive relationship, meaning that forward populations increase in abundance over time, while equatorial populations are actually declining. But what we're interested in this study is understanding, something just changed a bit, what about the range shift velocities? How do they relate into this story? And more precisely, is how does abundance relate to range shift velocities? And I'm asking this because we know that some species are slow shifters moving in rates of about 1 kilometers per year towards the poles, while others are quite fast shifters moving about 40 kilometers. In terrestrial environments, we can also find much faster shift rates as well. And we ask, do those slow shifters are prone to decline in abundance over time because perhaps they cannot keep up with pace of warming? And on the other side, those warm shifters may find stable abundances or perhaps even increase in abundance over time because they can. And furthermore, we try to understand how does the spatial position relate to the entire story. Perhaps forward populations behave differently than equatorial populations. So to start examining these kind of questions, we constructed a simplified null hypothesis because we undergone many scenarios, and it was really complicated, and we tried to simplify things. And we have here, first of all, a range of hypothetical species, and you can see here its leading edge, which is the forwardmost edge of its range, and the trailing edge, which is the equatormost edge of its range, and some different populations. Each circle, it's a different populations, and it's the circle size corresponds to the population size. And in blue, you can see forward populations, and in red, those equatorial populations. So now we'll try to understand how does abundance relates to range shift velocities. So we might first have the range distribution of the species in T0 before the warming. And we can see that we have a unimodal curve according to the abundance center hypothesis for simplification. And we can see that the forward populations are smaller than those center populations, that most of individuals are within the center. So after a range shift, we may predict 3 different scenarios. The one will be that there is no range shift for the specific species, and the abundance will remain quite the same. The second scenario is a slow shift, meaning that the forward populations might increase in abundance with respect to the T0. Center populations should slightly decline, and equatorial populations might drastically decline. And this effect gets only stronger and stronger if we're talking about a fast shifter. So finally, if we summarize the relationship here, we have on the y-axis the population trends with positive values for populations that increase in abundance over time and negative for those that decline. And on the x-axis, we have the shift velocity. So forward populations, bless you, should increase in abundance. Center populations should slightly decline, and those equator populations might drastically decline and perhaps even extirpate from a specific region. Okay, so how can we examine this kind of hypothesis? We bind two global databases. The first database is called BioShifts, and it measured different climatic-induced shift velocities. And the second data set is called BioTime, and it measured abundance time series of different populations worldwide. So first of all, I would like to take this moment to thank those publishers of these databases that made it public and allowed us to explore this relationship. So thanks. And after combining these two databases, we end up with 2,572 different populations belonging to 146 marine fishes. And they were spread relatively worldwide. Most of them are in the North Atlantic, some in the Northeastern Pacific, other in Oceania, and some other sporadic populations. Great, so now we have the data, and we can examine the relationship between population trend, the slopes on the y-axis. This is the slope of abundance against time. And on the x-axis, the different shift velocities of the species in kilometers per year, and the positive values are for species that move towards higher latitudes, and negative values for those that move towards lower latitudes. And what we found was actually a negative, significant negative relationship, quite the opposite than we thought, because those fast forward shifters are actually declining. And we thought that those fast shifters should perhaps sustain their abundances, or perhaps even increase because they are fast shifters. So I guess as most macroecologists, the next step will be to conduct many sensitivity analysis and check the robustness of this pattern. And first of all, we thought that this pattern might be driven due to those extreme shift velocities. So as a first stage, we removed those extreme shifts. We ran the analysis, and we found out that it's still significant and negative, and the slope became even a bit more negative. So we find no evidence that this relationship is driven due to those extreme shifts. Next up, we know that some species in our data set are represented by many populations, while others are represented by only a few populations. So it also could be that the patterns are driven by those species with many populations, and thus we cannot really generalize what we find. So what we've done here, we averaged the population trends by species and reran the analysis at the species level. So on the y-axis is the mean population trends for each species, and what we found is still a significant negative relationship. So given this data, we find that this pattern is relatively robust. As a next stage, we wanted to understand how does different populations respond to this relationship. So this is where we add the spatial position. So positive values are for populations that were sampled in the forward side of the range, and negative values for those that were sampled in the equatorward side of the range. And I just would like to note here that we do not have, our data is not represented mostly by those populations at the extreme leading edge or the extreme equatorward edge. And it's important because I guess all of us expect that at the extreme leading edge, we will find colonization and populations should increase, but we do not investigate these regions. Most of our populations are within the known species range. So just a small note. And the next step we've done is running interaction between shift velocity and spatial position. And what we found was a significant interaction, meaning in this case, you can see in red those equatorial populations that are relatively stable, not really matter what is the shift velocity of the species. And that was also counterintuitive to us because we thought that those equatorial populations that are also in the warm edge of the range might decline due to perhaps adverse warming. But we see a stable trend. And we thought that perhaps it could be related to climatic depth. So we cannot really assume that those equatorial populations are fine and they are persisting and it's great. We still, in my eyes, need to keep monitoring those populations. And we also know from different studies that climatic depths are indeed something that we find support of in marine fish. poleward populations are those that decline with increasing shift velocities, and that's kind of in accordance to the main pattern that I just shown you before. It could be driven by those poleward populations. And if I come back to our hypothesis, and we said that we have an abundance center, we work according to the abundance center theory, we actually might find, if we imply our results, we find that the abundance center hypothesis might not work in this case. It could be more of a poleward skewed distribution. And indeed, there's a kind of a great bulk of literature suggesting that the abundance center hypothesis, in many cases, doesn't really work. Another analysis, the final analysis that I'll show here, examines the relationship of different commercial status. So we know that fisheries may impact population trends, and we categorize the species to low and high commercial values, and we run a three-way interaction term between shift velocity, spatial position, and the commercial status, and we find a non-significant interaction, meaning that the relationship of population trends on shift velocity and spatial position, we have no evidence that it changes according to the commercial status of the species. We can see, for example, that poleward populations are declining no matter to the commercial status. And I don't have time to show further analysis, but I can discuss it later. But we also investigated the vulnerability of different species to fishing. But I would be happy to talk about it a bit more later. So to summarize it up, marine species track climate much faster than terrestrial species. We have many studies that showing these patterns, but I think one of the main messages of this study is that being a fast shifter doesn't mean that you're a climatic winner. And I think it's something that we need to keep investigating. It could be that those fast shifters are actually climatic losers. And if we try to give a more applicable message here, then range shift velocities can inform the conservation of local populations. For instance, if you're a marine protected area manager, or if you are a fish stock manager, of course you need to know which species you have in your range, but not only that, you may also need to understand what do we know about the range shift velocities of those species? What do we know about the population, the spatial position of those populations? And it might have a great meaning. And poleward populations might require special attention. So thank you very much for listening. If you have any questions, I'd be happy to answer them.